My name is Colin Heron. I'm at Newcastle University, and I'm part of a group which, working with the School of Mathematics and Statistics, are looking at the challenge of how many charge points do we actually need for the electric vehicle revolution in the world and the UK specifically. Since 2009, the UK has been installing electric vehicle charge points. Interestingly, for a conversion of 35 million vehicles, we have no national strategy for doing so. This is not just the case for the UK, it is for the case for almost every country in the world. What we are trying to do is to identify what the actual noise is and quantify the noise, and then we can develop a model to address this problem. We will be following this up with another paper using a 5-year study in a major UK city. One of the things which is not always understood is there is not one type of charger. So we have to understand what is the type that is required by size and power requirements. The second thing is where should these drivers go to charge? What land is available? Is there actually any power there? What is the demand for charge points now, and what is it likely to be in the future? And what and how will the driver do this? Many times you may hear on the news or read in the press that there is a statement which always comes out that we need more infrastructure. Whenever I ask the question, how much is more? Nobody ever responds. When I see some articles saying the UK or Germany or somebody needs 1 million charge posts, I always write and I say by type and by when, and how did you come up with that number? And again, nobody responds. The driver themselves want convenience, reliability, availability at an acceptable cost. But what we're looking at is, but what type of charger, where, how many are required to meet the demand at a point in time? We know that electrical energy is stored on board in EV batteries recharged by connecting the vehicle to an external electricity supply, which has to either be the grid or a storage facility. So the vehicles themselves can charge at or close to the home. I will say that I've had a full electric vehicle for over 8 years and mine charges at home. They can also charge at destinations such as sports centres or supermarkets, at workplaces, in public places, in transit on motorways. So there's more options available for an electric vehicle than there is for an internal combustion engine. We are watching through the diffusion of innovations theory, the adoption of the vehicles across the world. Norway is very advanced, and the UK has about 1.5% adoption across the whole of the volume of vehicles in the UK. The current position of the UK is confused by people referring to the percentage of sales. The percentage of sales is interesting, but when we have a market which is collapsing with returns of diesel and petrol, by default, if no extra sales of EVs happen, the percentage goes up. So we can see on the graphs here that the top left, that the percentage is going up, but the numbers are still very small. So in 2020, the total number of electric vehicles or vehicles with a plug that were registered new in the UK was 175,000. Bearing in mind we have 35 million vehicles. You will see in the bottom left, the graph is showing that actual numbers are pretty stable going forward. Even though we get a large increase in percent, that percent is not a large increase in number. In all of the countries so far, in all of the cities in the world, every prediction of EV volumes has been wrong by large factors. because this has been done on projected sales in political announcements and not on other factors, which I will go into. The options which people have now are they can charge at home, they can charge on the street, they can use high power chargers, and there are now drive-through filling stations. 9 years ago, there was only one choice, which was a 3 kilowatt charger. We now have 350 kilowatt chargers. Charging time was 8 hours, it's now 40 minutes. This is to exemplify the challenge that we have, where Milton Keynes has over 100 high power chargers for 250,000 people. My area has 30 for 500,000 people, and Cardiff has 10 for 350,000. Now the question is, what is the logic of the number of chargers required in those cities? If we divide the country up by charge points, we will see fairly equal division, except London. And we also have a plethora of providers from the private sector as well as the public sector. The next point is the behavioral analysis, which we are looking at. There is a preconception that every electric vehicle driver will plug in at 6 o'clock every evening. Our recent study of when people charge shows that around 25% charge every day. But a large percent will charge on most days, but we have 40% of people charging a few times a week, then once a week and a few times a month. What we have seen is the range of the vehicle has extended. So my first vehicle 8 years ago did 86 miles. My second vehicle did 100 miles. My current vehicle does 250 miles. My behaviours due to COVID have changed to working from home. So I'm actually charging my vehicle every 3 weeks. When we do big studies of local authorities, we've started to find that not only are people not filling their vehicles fully at charge points, we are seeing differences even between local authorities. So the top set of figures in the blue is Manchester versus the northeast of England, and the amount of power is different from different regions. We've also been looking at where do people charge. Initially, it was 80% at home. Now it's 44% at home. Almost none were at work, and that's now up to 22%. So as the vehicle technology changes in terms of battery capacity, what we are seeing is the everyday charging is not every day anymore. Where people charge is varying as the options appear, and the amount of power they are taking is changing in terms of another variable. We're also seeing situations where in some areas, the public charging is dropping. In some areas, it's going up, but very slowly. One of the considerations was the price. So some local authorities initially had free charging, which attracted people to park. When that came off, things changed. There is one graph there which clearly shows the utilization of the public network is going down dramatically, whilst the number of vehicles is still increasing, because the charging habits have changed based on pricing. We have this virtuous circle which was designed by the government that subsidies would increase sales, which would increase the demand for charging, which would lead to more chargers. The number of EVs is going up very, very slowly. The subsidies is falling. And the logic is, unfortunately, that because the demand for the chargers would go down, then the number of chargers going in the ground will go down. This is not happening because the UK and many other countries believe the more chargers that you put in, the more vehicles you will get, which doesn't correlate. We have now got another bit of noise in the variable, is the pricing structure of each of the different operators is also driving habit. Looking at these figures here, we can now see by the type of charger when people are using this infrastructure during the day. So we've got projections of EVs using various models, whether it's the national grid, our own models. We are seeing the charge events by rapid chargers, fast chargers. We are seeing which days of the week people are charging. And the graph on the right, which is of interest, shows the COVID effect, where people just stop commuting. But what we're seeing now is there is a secondary COVID effect, where people have changed their driving habits. If we look at the vehicle technology, for high power chargers, there is a charging curve. It's not linear. So the curve starts at a low level, and within about 30 minutes, there is 80% of charge. Unfortunately, the last 10% takes 35 minutes because of the way the battery in the charging system is designed. The power delivery depends on every vehicle model, not the vehicle. So in this case, you can see that for different models from the same manufacturer, it takes high power longer before it drops off. So if we have something like a 50 kilowatt charger, it doesn't deliver like a petrol pump, a linear amount. It's dependent on the power curve. So for Nissan vehicles, they actually take just over half the power of the designated delivery machine. So there's some very low power at low time at high power. On other models, they're taking a lot of power, and so this has an impact on the grid. So if you look at vehicles back to back when you arrive at a charger, and we look at an ideal scenario, which is the same type of car follows the same type of car in a queue to a charger, you would get a sort of sawtooth pattern where it will be high power, it will drop off, change over, high power, drop off, change over. Unfortunately, every vehicle is different on that curve. And it is also up to the driver on the curve at which point they want to fill, which means every single charging event in a high power charger is a unique event. So these are some of the examples of the curves for every different vehicle. And these were the first cars on the market. So you can see their maximum power is 50 kilowatts. We're now starting to see new vehicles appear. And you can see on here, the figures are around 150 kilowatts. They're taking much high power quicker. This is again changing behavior. I've superimposed the power of the Nissan Leaf, the one that I used to have. So unfortunately for charging behavior, most of the research papers to date are not valid because the vehicles are actually obsolete. This leads us to the impact of variables. So when we look at volumes of cars, we know roughly how many vehicles are coming to market. But what we do not know yet is what percentage of people charge at home, at work, or in the equivalent of petrol stations at high power chargers. So for this case, I've just put in 20% high power charge. We know there's 24 hours in a day, but what is the charging window? And if we go back to those curves of when people charge, people are not charging at 1 o'clock in the morning or 2 o'clock in the morning. So what we get is people have a desired window when they want to charge. So if everybody queued up nicely for a 1 hour charge, we would do 24 people on one charger per day. If 24 people all want to charge at 1 o'clock, we need 24 chargers. And the other very big variable is how long people actually spend on that charger. And we're seeing that's varying between city and rural. So the actual time on there is a big factor. And then the frequency of charge. So on the graph on the right, this is just using different variables from user behavior is the number of charges which could be required in a town. And it can vary from 30 to 140. Now these charges are £25,000 a time. This is an installation which was publicly funded in Coventry. However, there are only 419 electric vehicles registered in Coventry. If you substitute that into the table I've just produced, we have a 2.5% utilisation. So these charges have been put in with that utilisation. Now, in one of the world studies we have to look at is the question of, do we put in lots of charges to get vehicles or not? And this interesting study here shows that in America and Oslo, they put in few charges and got a lot of vehicles. Paris, London and Amsterdam have put in a lot of charges for less vehicles. And in China, they've put an enormous amount of charges in for roughly the same number of vehicles as they got in Los Angeles. So we can see the average ratio here. So what we have to look at is, and this was from Hall and Nutsey, is what is the projected number of vehicles that we're actually going to get on an annual basis? And that is governed by the number of batteries, the price and the availability. Who's going to be driving these vehicles initially? Is it taxi drivers or is it the public? Is it the retired public? Is it the middle class public who can afford them? How much energy will they need and from where? How will the charging speeds affect this? How long will they be charging? How many charges are required? And as you can see here, these are the primary factors which we've been investigating to try and come up with this model which we'll be applying to a large city. Bang on 20 minutes.
Good afternoon, everyone. My name is Lais Wehbi. I'm a PhD candidate at the University of Liverpool, specifically in the Department of Operations and Supply Chain Management, and I will be presenting our work with Tolga Bektas and Cagatay Iris on assessing on-foot porter routing in urban delivery networks for environmental impact. So to kick off, just to take you through the outline today of the presentation today, firstly, we have the introduction where I will talk about what is last mile logistics and how it is relevant to our current urban environment. Then I will cover some of the last mile models seen in the literature that involve the use of alternative or green modes of transport. This will then lead to the problem description where I will take you through some of the parameters and decisions involved that lay some foundations of our model, and then we present the mathematical model with its objective function and constraints. The mathematical model will then be solved using real data, and we show this in section number 5 in the computation results. And finally, we conclude by giving prospects and opportunities for future work. So to start, the e-commerce retail industry has grown drastically and has gained significant traction in the past decade. In 2020, the retail e-commerce sales worldwide amounted to $4.2 trillion US, and this is only forecasted to grow to 6.3 trillion by 2024. Now, in the UK, a total of 2.8 billion parcels were delivered in 2019. This was an increase of 209 million parcels compared to the previous year. Now, from a carbon emissions point of view, the transport sector has now overtaken other sectors as the highest carbon emitting industry compared to the other industries. Now, this increased number of parcel deliveries has resulted in the prominence of last mile logistics, and last mile here is referred to the last leg or last part of the journey an item makes before it reaches the consumption point or the consumer. And this is usually reported that accounts for 41% of e-commerce supply chain costs. Now, typically, these last mile activities are carried out with freight transport vehicles, such as vans, trucks, and lorries. And in 2017 in the UK, we saw that the freight transport vehicles lifted about 1.41 billion tons of items, which also equates to 152 billion tons of kilometers moved, and also equating to 18.7 billion kilometers traveled. Now, if we look at this at an urban perspective, in a city perspective, we can see that in 2014, the 16% of the total road vehicle activity in urban environments was from freight transport vehicles. And this equates to 3% of the total carbon emissions in the UK in 2014. Now, typically, such emissions from last mile activities can be improved with the use of optimization models or greener modes alternatives. The last mile dilemma in an urban context is, however, quite different, as it presents a certain number of challenges that are only exclusive in an urban environment. Some of these are limited curbside parking space, time-sensitive deliveries, inner city road restrictions such as low emission zones, and traffic congestions. Now, we will look at some of the models from last mile literature that attempt to overcome these urban challenges. Now, if you can please divert your attention to the table on the right, it summarizes some of the most relevant contributions to urban last mile. Here, the model type, objective, and transport mode is highlighted with a solution, whether it's an exact solution, a heuristic, or whether a case study was implemented. It is observed that there are mainly 4 current streams of alternative transports that appear in last mile literature and are used in conjunction with vans. These are drones, truck and trailer, cargo bikes, and porters. Now, I would like you to please also shift your focus on the last transport mode, that is portering. Now, in case you didn't know, portering involves the use of human walking for the carriage of goods. So in other words, it is simply a person that is exclusively tasked with walking and carrying parcels from point A to point B. Now, I should mention that we do classify this differently to walking. So that's why in the column of the transport mode on the table on the right, you can see that there are some studies that mention vans with portering and some others that mention vans with walking. The similarity with this is that both require the optimization of walking sequences. However, their business models quite differ. With portering, we are using an outside entity to basically come pick up the parcels from the van or meet the van and pick up the parcels and continue on serving other customers. While with walking, it's optimizing exactly the delivery driver. So basically the van driver will have to park the car and he will have to come out and take out the parcels and he will have to go serve customers and then go back to the vehicle. Now, there are some notable studies here that we can look at. So Nguyen in 2019 developed special type of traveling salesman problem, or special variant of the traveling salesman problem, and it saw a 50% reduction in driving time when their portering model was implemented. And another notable study done by Martinez in 2020 saw that walking makes up a significant portion of the journey, meaning that there is some sort of potential to reduce the vehicle travel time and hence reducing carbon emissions. Now, this therefore, it can be said that most of these studies that implement portering or walking collectively focus on overcoming curbside parking restrictions, including time window constraints, and quantifying carbon emissions, and focusing on carbon emissions. We therefore contribute to the literature by proposing a new portering model that takes into account the following. Firstly, our first model aim would be to overcome curbside parking restrictions. Secondly, the model would determine each delivery mode for each customer, whether that is a porter, whether it's being served by a porter or a vehicle. Thirdly, we account for time windows. And lastly, we have to generate an environmentally friendly distribution plan where we quantify the carbon emissions as well. Now, to shed some further light on our problem, I will briefly take you through an example solution of our model. Now, suppose we have a set of customers, 17 in this instance, that can be served by either modes of transport, either the vehicle or the porter. In the first echelon, or the first level, we can see that multiple vehicles with limited capacity leave from the depot to serve customers and handover points. Now, in this instance, we have exactly 3 vehicles leaving from the depot. Sorry, I'm not sure if the laser is currently showing, but I will just use that. Sorry, can you see that? Apologies, I'm not sure if I can see the laser pointer. Yeah, okay, I believe I can. Yeah, okay, perfect. So in this instance, we have exactly 3 vehicles leaving from the depot. So 1, 2, 3, and they either serve handover points at customer selected locations or just customer points between between specified time windows. Now, if a customer is selected by a model as a handover point, then parcels are transferred. In this instance, for example, parcels are transferred to the porter by the vehicle. Therefore, these handover points that occur at these customer selected locations act as a swift rendezvous point where the vehicle hands parcels to the porter, and then the porter continues to serve other customers. In this case, we can see that the first vehicle, as I said, goes and serves the first customer and then goes and to handover point at the customer selected location. It serves the customer at that point, and it meets with a porter, hands over the parcels, and the porter goes on and serves customers and does not go back to the handover point, nor does he or she go back to the depot. And the journey is completed once all the customers have been served by the vehicle and the porter. And this therefore takes us to the modeling aspect, where we formulate our mathematical model as a mixed integer linear program. Now, here we have the objective function of our model is to minimize the distance traveled by the porter and the vehicle. This is subject to a different set of constraints. Our first set of constraints is the vehicle set of constraints, which include flow and route conservation constraints, such as the number of vehicles must not exceed the number of the number of vehicle routes must not exceed the number of the vehicles, and also the total load of the vehicle leaving the depot must equal the demand of all the customers. And we have another set of constraints for the porter and handover, such as porter routes are only created if there is a handover point, and each customer also can be assigned only 1 handover point. And lastly, we have time window constraints, where we specify that customers have to be served in a preferred time window. Now, for the computation results, now we code our model into Cplex, an optimization software, and we solve it using a real data set containing 57 customer locations based in central London, and they include pairwise travel distances between each other. The demand profile for all the customers is randomly generated for each size, and the model run time is set to about an hour, as we believe that provides a good indication of how long planners can wait before deliveries can start on the day. Now, for the first experiment, called randomly selected customer locations. Now, from its name, customer locations are picked at random and to form a matrix which is plugged into the model. In this instance, we solve 20 customer locations, 25, and 30 customer locations. Now, showing the results of this, I would just like you to divert your focus on the bar chart here on the right, where it highlights the average split between the vehicle and the porter for 20, 25, and 30 customer locations. Here, the yellow part, or the y-axis, sorry, is the time traveled by both the vehicle and the porter. The yellow part of the bar chart is the time traveled by the porter, while the green part is the time traveled by the vehicle, excluding STEM, meaning that this is only within city boundaries or in an urban setting. This does not include any areas that do not fall within the city center area. And as we can see that across each instance size, the porter contributes about 50% of the journey time in some instances, meaning that the porter has a high significance when it comes to the total journey time. Now, this translates into affecting or making a difference with the van travel time or the vehicle travel time. Now, this table simply shows the van travel time with using our model and without using our model. So on the y-axis, we have the same time traveled of the van, and we can see the green is without our model, and the yellow is by implementing our model with portering. And as we can see, also it follows the same trend as we saw from the results previously. there's about a 50% reduction in time and in use of the van, of the travel time for the van. This obviously yields reductions within carbon emissions, which I will talk about or highlight in the next couple of slides. Now, to illustrate the Porter's significance, we have to look at a solution plotted on OpenStreetMaps. Here we can see that a vehicle 1, represented by V_1 here in this case, or the blue line, it goes and serves 2 customers here, serves 2 customers, and then meets with a porter represented as P_2, or red-orange line. It overlaps here, so it's not very clear. Apologies for that. But here, the handover points are also indicated by the capital letter H on the porter label. Now, the second vehicle, which is on the green route, V_2, serves a couple of customers here before meeting with various porters at different handover nodes. But one thing to observe here is that the model is choosing to utilize the porter on side roads here in some instances, while the vehicle is being utilized on main roads. Now, this could be due to the different directions of the roads and just the overall ease of access. Now, our third experiment here, or our second type of experiment here is the capacity differentiation testing here. Here we are simply testing the capacities of both the vehicle and the porter. Initially, we set the vehicle and porter capacities as 100% and 25% respectively of the total demand. And then we start reducing gradually, and we start to observe the changes that happen within the routes or the utilization of the porter. And we test this only for 20 customer locations, but it gives us a good indication of how the porter is being used. So this graph on the right shows the porter usage on different capacities. So if we look at 25% here at porter capacity, it shows us the different, these lines indicate the different vehicle capacities. So we can see at different vehicle capacities, the porter travel time differs slightly. However, one interesting thing to note here is that as we reduce the porter capacity, we can see that there's a slight increase in porter travel time. What this simply means, or what this simply suggests, that even at low capacities, porter usage can be quite high. So porter is significant even at low capacities on different vehicle capacities as well. Now, from these experiments, we saw that there were various time savings from using a porter. Now, these time savings can be converted into distance using a velocity, distance, and time equation, where we account for the different velocities or speeds of the van. Now, the distance savings are then translated into carbon savings through the use of the European Environmental Agency model. The EEA uses a predicted fuel consumption rate along with an emission value according to the type of vehicle. For this case, we assume that the type of delivery vehicle we're using here is a petrol diesel Euro 5, and we calculate the carbon dioxide savings accordingly. And as you can see from the right graph here, we can see the right y-axis of the graph shows the carbon dioxide percentage saved, while the left y-axis shows the carbon dioxide saved in grams. And obviously the x-axis is simply the customers and the instances being solved. As we can see, the carbon percentage saving ranges from about 37%, I'd say, to 89% in some instances. This also shows that the porting is quite relevant and is able to massively reduce the carbon being emitted from the reduction of the vehicle travel time. Now, finally, to conclude, we've introduced a mathematical model that integrates the green mode of transport, that is portering. And this was then tested on real deliveries that are located from central London. And we saw that the model achieves time and carbon savings of up to 50% and 89% respectively. However, there are various considerations needed to make the model more realistic or to improve the model. Some of these are, the first one is, the model does not factor in the weight and volume of parcels. Now, this is quite important with portering, especially that porters they have very limited capacity as they are carrying bags or parcels on their back, supposedly. So this is quite important to consider. The second point is that hiring labor costs for porters is not considered within the model. This is also important because the model can utilize as many porters as it likes, and this is not a very realistic scenario to be in. And lastly, The model only solves up to 30 customer locations with near optimality, and a heuristic would help. A heuristic would be suggested to help improve that cap and help solve that much quicker. Thank you for listening, and please feel free to ask me any questions. If you have any follow-up questions, please email me in this email below.